Hello and welcome to CSE 228. Today we have a special guest lecture from Frans Skarman, a PhD candidate, literally days from finishing at Lushing University in Sweden. So today he's going to talk to us about Spade, which is a language we're all really excited to hear about in Agile hardware. But you also may be familiar with Fran's work making the Surfer waveform viewer. So I think it's commonly used by a lot of you. So yeah, and I see faces in the audience being excited. Yeah, the legend is here. So yeah, with that, we'll please let Frans take it away.
Thank you. So my name is Frans. My thesis is due on Monday, so very much at the end of the journey here. I'm talking about Spade. This title is kind of outdated because I'm reusing some slides. Oops. But yeah, I'll talk about Spade. Surfer is my other project. Apparently, you've heard of it. That's fun to hear. But yeah, Spade is my sort of less known project and perhaps the one I'm more excited about, even though Surfer is more successful. So Spade is an HDL. I think a lot of the new HDLs being developed are all about sort of this agile hardware design that, as far as I understand, this course is about. And I think a lot of HDL sort of approach this agile hardware design idea in many different ways. Chisel approaches it of like, we take a software language, we give you the software language as metaprogramming, and with that you can do all kinds of cool stuff. And that works really, really well. But I think there are other ways, other things we should explore as well, because it ends up being a little bit clunky in my opinion. Chisel has a really good type system, but it doesn't have a type system that is available in hardware. It only gives you access to the type system during elaboration time, which is great, but I also want a type system in my hardware designs. And so if you're sort of after the building a chip generator or something like that, something like Chisel is hard to beat. But if you're more building an accelerator, a specific accelerator, or sort of communication protocol stuff, then I think Spade might be a nice alternative that has some advantages. I will say as well, if you have any questions or comments or anything during my talk, just shout them out. I would say raise your hands, but I can't see your hands. So shout out questions. Please interrupt me. The presentation is a whole lot more fun if it's interactive between us. Um, yeah. So I am a software person originally, and then I ended up in hardware, and I was sort of appalled at the state of tooling in the hardware world. And I always wanted to build a programming language, so I figured, why not build a programming language for hardware that takes ideas from software and sort of incorporates them in a nice way in hardware. And one of the things I really enjoy about software languages, you'll see Rust is a great inspiration for Spade. And one thing I really enjoy about Rust and a few other languages is what I kind of call fearless refactoring, where you can take a large project, you can decide, I want to make an invasive change to this project. You make the change purely mechanically, following the advice of the compiler. And at the end of the day, when you've made all your changes, the code should still work. You shouldn't be afraid to make major changes to your code base because that's how you end up in legacy code land. Um, an anecdotal story I have here is replacing a library we used in Surfer. We used to have a waveform parsing library that we replaced because Kevin Laufer wrote a much better waveform parsing library. And so that was sort of a central library that was throughout the project that we wanted to replace. I did this by sort of picking a point at random in the code base and making the change from one library to the other. And then made that change, recompiled, fixed the compiler errors, recompiled, fixed the compiler errors, recompiled, and so on. And this took about 8 hours. I had 6 hours of sleep, so I wasn't paying attention. I was just mechanically doing this. And at the end of the day, after about 8 hours, I had a diff that was about plus minus 2,000 lines of code, which worked on the first try. The first time it compiled, the thing worked. And now I'm not claiming Spade is there for such an invasive change, but I think it's certainly something we should strive for, of being able to make large-scale changes to code without being afraid, right? I think software does a really good job of building abstractions around the things that matter to whatever a programming language is designed for. Again, going back to Rust, because it's what I know and love. The reason Rust is able to have memory safety is they realized that the problem with memory is that you're sort of managing it all manually. Um, with very little help from any abstractions of the compiler. So instead of managing pointers and allocations, we change it to managing ownership and lifetimes, and that allows the compiler and the user to reason about things in a different way. And by doing that, these new abstractions allow Rust to essentially eliminate the problem of memory safety. Again, this is kind of a thing where it doesn't really work in hardware. Like we can't do ownership in hardware and expect something good to come out of it. Instead, we need to go back to the principles behind this of building abstractions that hide the sort of difficult details or wrap the difficult details in something that is easier to work with. But also because we're building hardware, we kind of have performance requirements. So these abstractions need to still show the need to give control over things, but they need to sort of reformulate the problem in a way that that is easier to reason about. And then like tooling is something I'm kind of obviously very passionate about. I think software has really good tooling. Sort of all new modern programming languages have very good tooling. Hardware very much does not have good tooling. So if we want a good hardware description language, we need good tooling to go along with it. All right, so that's sort of my pitch for Spade. We steal stuff from software and everything is nice. Let's get into some details of things we can do. One of the first things I designed into the language was a concept of pipelining. Because I realized that pipelining is something that, while it isn't super difficult to get right, it is quite tedious. And it's a problem that is simple enough that we can sort of build a very nice abstraction around it that just solves the problem outright. And this is what it looks like. I have some code for a pipeline on the left, and I have the corresponding hardware on the right. There are three interesting statements in this code. The first one is the pipeline of 2. The 2 is the latency of this pipeline. So because we are talking about a pipeline and not just a collection of registers, we now know that there's a fixed latency to this. And by just reading the head of this pipeline, we find out what the latency is. We don't need to look at the body. And that's great when you're instantiating this, and it's great for the compiler because it can check our work. Then inside the body of the pipeline, when we want to have a stage, we put a reg statement, and it will essentially take all the registers, all the variables above the reg statement, and put them in registers. And then when you refer to them below the reg statement, it will refer to the registered version. So this x here, for example, will not refer to this x, but the x that has gone through a register. And you can see quite clearly that there's a sort of one reg corresponds to one cut in the graph here, and one reg corresponds to a cut in the graph here. I'm gonna do this so I'm distracted. Okay, so this is kind of nice when you're designing your hardware. You don't have to sort of add a bunch of intermediate variables that don't actually have any effect. But it's a lot nicer when you need to refactor this code base or this pipeline. And say we do some agile hardware design. We thought that we could do G with a combinational circuit. So this block could be done with a combinational circuit. But as we implemented it, we realized that no, we need to do more in G, or we overestimated what we can do in G. So we need to make G into a pipeline as well. And we need 2 stages for whatever reason. And then our circuit will end up like this. And you can probably already spot an error. But the nice thing about Spade is that you don't need to spot this error manually. Because what you will do is when you compile this code with the change G, the compiler will first tell you that, okay, G is not instantiated as a pipeline, it's instantiated as a function, which it was, but it's not anymore. So first we need to change the instantiation of G to say, this is the depth of G. And now the compiler will check our work and see that, yes, that matches. G has latency of 2, and we instantiate it with 2, so everything is fine. And so we recompile, everything is not fine, because you probably spotted it already. This back edge means that the circuit will not do what they did originally. It will probably compute a bogus value that we don't actually want. So what we can do so what happens is we don't need to look at the figure to see this problem. We run the compiler being aware of how pipelines works and how latency works, will tell us that X is not available yet. You need to wait another clock cycle, or you need another stage in between the instantiation of X and the use of X. So it gives you this compiler error, which admittedly, now that I look at it, could use a little bit more of a suggestion now that we have suggestions in the compiler. But either way, it gets the information across. To make the change, again, because pipelining is a native feature in the language and something that you and the compiler can reason about, you can simply add another, oh yeah, you want to make this change to the pipeline, and you can simply add another reg statement over here. And you, of course, have to update the head of the pipeline as well. And the compiler will tell you if you forget. So now that you've done this, you recompile. If someone else is instantiating this pipeline, they now need to update their code. And in that way, we sort of purely mechanically change the latency of this pipeline, of this inner pipeline G, and the program will still behave as expected, assuming we don't care about specific latency, of course. But hopefully we've written our code, instantiated this pipeline in a way where it's either instantiated in another pipeline, so latency is taken care of, or it's instantiated somewhere else where latency isn't a problem. And even if it is, this inst2 will still make sure that when we wrote the code, that we check back where we instantiated the pipeline to see that, okay, did this affect anything? So that's pipelining. There are some other features in pipelining as well. You can sort of refer to other stages. That way, a few guarantees go out the window, but you can still use the pipelining construct for something that isn't a straight pipeline. Like you can use it to build the data path of a CPU where there's lots of sort of packages and stuff like that. Yeah, so that's pipelines. Can I just ask, are there any questions on the sort of pipelining thing?
Yeah, we have one.
Yeah, so
All right.
when you
Shoot.
when you have a pipelining error like this where you have a required extra cycle, how are you detecting that? Like you're just detecting that by looking at like when the compiler looks at this, is it looking at a graph representation and then seeing that package, and then that's how it knows, oh, you need an extra cycle for this?
So it's not looking at the graph. It's sort of looking at the pipelining structure. It keeps track of X is instantiated with a latency of 2 here, and it's being used. So it's instantiated here. So then it says, okay, I need to see 2 reg statements before you're allowed to use X. And so if it only sees 1, it will tell you that, yes, it's not available. If it sees more, it will tell you that, or it will let you do it. And it will also not add any registers at the end of G. So, but yeah, it's not looking at the graph. It's looking at this staging, essentially.
Great. Other questions? Okay, maybe continue.
Yeah, absolutely. So that's pipelining. As I built out the language, I've added a whole lot more things. So there's other ways of writing other things now. And one thing that I've recently got into a state that I'm very pleased with is sort of latency insensitive interfaces. And with methods and latency insensitive interfaces, we can do things like transforming protocols between each other, essentially mechanically as well. So one of the things I've been playing around with is having a Raspberry Pi camera, taking the camera feed from the Raspberry Pi camera, and doing stuff with it. And so the decoding of the Raspberry Pi camera is kind of uninteresting. I won't show it here. But I then wanted to take all the nice bytes from my Raspberry Pi camera and send them over the Ethernet. And so this is how you can do that. And sort of, if you just read the documentation on the camera library and the Ethernet library, you might find that, ooh, there is an inter-Ethernet bytes method somewhere on something. Let's try to run that. Because again, I'm a software developer. I read the minimal amount of documentation and then try whatever happens, or try whatever I find and realize it probably isn't going to work. And so in this case, the compiler will say, okay, you have a option of t, which is essentially a signal with a valid tag. Those cannot be turned into Ethernet bytes. You can only turn things with a ready valid signaling into Ethernet bytes. Because the camera is kind of shoving data at us at whatever rate it pleases. To send them over Ethernet, we need to send them at exactly 125 megahertz for 1 gigabit Ethernet. And so there's a mismatch. Somewhere in this chain, we need to sort of break the stream of bytes into something we can control the rate of. So, okay, we have an option. We want to turn it into an RV. We can do that with a FIFO. So we instantiate a into RV FIFO method on the option type. The option type is defined in the standard library. The RV will be at some point. It's a separate library now. But we instantiate this RV FIFO. We also, knowing something about Ethernet and packets and stuff, know that we kind of have to packetize this data into network packets. So we'll do that here as well. The compiler would tell us if we didn't, right? And so now maybe we can just into RV FIFO packetize things and send things as Ethernet bytes. But now the compiler comes back and says the type RV of pixel packets doesn't have a method into Ethernet bytes, but there is a method for RV of IP packets. So what it's saying is essentially you can't just shove random packets over Ethernet. You kind of need to wrap them in something that Ethernet supports, or the other side will understand. And so if we go back to our sort of networking class, we'll know that Ethernet is sort of a layered, or the whole internet stack is a layer of protocols. So at the bottom we have bytes. Bytes have our Ethernet packets. Those have a header, and then there's a payload. That payload is an IP packet that has a header and a payload that is a UDP packet that has a header and a payload, and so on. And so in the Ethernet library, there are methods for just converting, or no, sorry. We have to write a method for converting our application packets into UDP packets. And then we can just use the provided methods for converting into IP, specifying what IP addresses we want to use. Probably we should have one of these two shouldn't be the same. But yeah, we turn them into IP packets. We turn those into Ethernet packets. And now we can turn them into Ethernet bytes. Okay. Problem is, we're writing hardware, and we forgot that we're writing hardware because we just chained a whole bunch of methods together. So it's quite likely that the critical path in this will be somewhere in this method chain. And now comes another advantage of doing this with methods, is that the methods sort of transform the payload or transform whatever the ready valid stuff has, independently of what is underneath. So we can also have things that do hardware stuff like buffering. So we can buffer the headers and we can buffer the Ethernet bytes, and we can insert those independently and move them around independently of our sort of computation that we're performing on the packets. So by inserting buffers where the synthesis tool tells us that a critical path is, we can now get something that will work. This will transform my camera data into Ethernet bytes that I can actually send over to my laptop. So an obvious question here is, what is a method? Well, essentially, a method is just an instantiation of a module. So this is the corresponding Verilog code. There's a whole bunch of stuff here of like signals going both forward and backwards, which I think you can do in Chisel as well. But in Verilog, you kind of have to separate the two. There's just a lot of stuff here. Nothing here is interesting. Nothing here is something you need to control. It's just something you have to control because you can't abstract over sort of protocols and stuff like that in Verilog. So there's significantly less code, and you don't really sacrifice any control, I would say. And if you did sacrifice control, Spade is an RTL level language, so you could replace these method instantiations with a lower level description if you need to. So what that essentially means is the corresponding Verilog is like really, really, really long and doesn't say anything. It's just pointless in my opinion. So, oh yeah. There's of course stuff going on inside these methods. I will actually talk a little bit about that later, but for now, inside every method is essentially a state machine that waits for packet sending to be requested by the layer above. They will then emit a header with the sort of layer below, and then just take the payload from the layer above and stream it through. So it's essentially just a state machine behind every instantiation here. So a few notes here. This isn't high-level synthesis. You know what you get, and this is the same thing with Chisel, right? One of my real pet peeves is when people say I don't want to use Chisel because I don't want to use high-level synthesis, because they're really not the same. Chisel and Spade and most other HDLs give you a lot more control than high-level synthesis. They add abstraction, but that abstraction usually doesn't take away too much control. And I like to think about abstraction in a diagram that looks something like this. Of a language has a minimum level of abstraction, like what is the lowest level that you can reason at, and then sort of a highest level of abstraction. What are the things you always kind of have to think about? High-level synthesis, you don't have to worry about timing, but you also cannot control timing. VHDL and Verilog, you get as much control as you want, essentially. But you kind of always, you're limited to reasoning about bits and operations on those bits. In Verilog and VHDL, you will never ever be able to ignore timing completely. And with Spade, I'm trying to kind of push the boundary of like sacrifice as little control as possible and move towards a higher level description where possible. Perhaps eventually we won't have to think about timing in every part of the circuit, just the ones that matter. We're not quite there yet, but I think it's something to aim for. And certainly without sacrificing this low-level control, we still want lower-level control because we're building hardware that has performance requirements. Let me see what is next. Oh yeah. So a few details on sort of the inner workings of this packet transformation stuff. Being a software developer, I look at this diagram and I'm like, there is a lot of code sharing potential here, right? Every layer is essentially just wrap an inner layer with a new header, right? So as I wrote this, I got like 3 protocols in, and then I was like, okay, I need to abstract something around this. So what I did is define a type for reasoning about header payload streams. So a stream that has a header and some payload. The header is sort of whatever, and the payload is bytes. And it's 2 separate ready valid handshake signals. And then we can add methods to this. So impl for any inner header, we implement a method for header payload stream. The method we're going to add is a thing called lower, which takes, let me see what the order this is. Yeah, so it transforms the inner header into a header payload stream of an outer header. And we have a few requirements on this. In order to be able to transform the inner header, we need to be able to turn the header from its sort of struct representation into a sequence of bytes. So we need to be able to serialize it, and we need to know a length, which is encoded in its header trait. So this is essentially placing requirements on what things we can wrap inside this header payload stream. And then there's a lower thing that really will become a lambda function once lambda functions are fully in the language. But for now, it's kind of a workaround around not having lambda functions. And inside this method, there is a state machine that essentially just waits. It waits for a packet of the inner header to arrive, and then it emits an outer header for that packet, then serializes the inner header into bytes and emits those, and then emits the payload of the inner packet, and then goes back to idling and waiting for more packets. And that's it. I hope that's like the most complex slide here. Hopefully some of it was understandable. The end effect is essentially that if we have a type for IP packets, we can define an into Ethernet function in that just uses this lower method in exactly the same way as we do for UDP to IP. So these are exactly the same. If you're building a new, like if you're building an application, you can reuse the same thing. If you don't want to use Ethernet, you want to use UART or AXI or something else, you can reuse this infrastructure for anything that is like headers and payloads. And that's something that I'm quite pleased with. Oh yeah, so the next part of the presentation shifts gear entirely. So if you have any questions on this, let me know.
Yes, we have a hand raised. Please go ahead.
Yeah, could you go to the previous slide for a second?
This one?
Yes, that one where you mentioned this part. You said you guys were planning to implement Lambda functions into the Spade. Could you like briefly go over what's your kind of current approach and process for doing that you guys are
Yeah,
thinking of?
absolutely. So one obvious requirement from the Lambda functions is that like dynamic dispatch is not happening, right? So I am essentially doing the same thing which Rust and C++ are doing, of you just define the struct that has a call method, essentially. And then with generics, you can call that call method, and for every Lambda function, that call method will do whatever the body of the Lambda function is. So it's all static dispatch, but at the end of the day, it's really a struct with a custom call method. Does that answer the question?
I see. Thank you.
Any other questions?
Okay, in person.
Okay. Let's move on to something else. So, yeah. So the option type is essentially in hardware, it gets implemented as a Boolean and the data it kind of validates, right? A tag and data that is valid if the tag is set or not. Looking at this type, we might be able to guess that this is a valid data thing, but we don't have any guarantees. And we could write a function that takes this as an argument and presume that someone will pass out something that is valid and a valid tag and data, but they could pass something else, and the application will probably break. So modern type systems have, of course, a solution to this, or I guess this isn't really modern. This has been around since forever, but it's new in hardware relatively. So if you're in Scala, I think you have the same type essentially. I don't know if it's called option, but essentially we can define a type that has multiple different representations of the bits depending on a tag. So we can either be some, in which case a value is present, or we can be none, in which case no value is present. There are some advantages to this. It is impossible to misuse this because the compiler will enforce checking the tag before checking the value. And this sort of means that, yeah, you cannot misuse this. If you get past an option, you can only handle it correctly. If you expect an option, you know that you will get an option. Additionally, the compiler knows that this is an option type. The compiler knows that whatever bytes, whatever this t is when the bool isn't, when the tag isn't valid, it doesn't really matter because the user will never look at them. And so we can start doing compiler optimizations because we've sort of given up control over whatever this value is in the clock cycles where it's not valid. And so as an example, if we have a register that stores an option type, that will have a tag that goes into, that will have the tag and a value, and that gets stored, and then every clock cycle, this block of hardware, whatever it is, in this case a multiplication, will switch. Even if the tag is valid, even if the tag is invalid, the data that is coming over here will still flip, and so we will consume dynamic power. A way to write this that saves dynamic power is instead writing this, where we use the tag to choose between keeping the old value or getting in the new value. And with this, we don't switch this unnecessarily. We won't switch it for invalid data. We'll save power. And looking at it like this, we'll probably sacrifice area because a multiplexer isn't that cheap. Luckily, if you write the RTL code that describes this circuit, your synthesis tool will convert it into something better. In a ASIC case, it will convert that into just a clock-gated register. So whenever the tag is valid, whenever the tag is invalid, it will not clock the register. In an ASIC, or sorry, in an FPGA, this will most likely get compiled down to an enable signal. In FPGAs, it's a little bit more tricky because usually enable signals are shared between a few registers. So if you have a lot of single bit tag value signals, then you might lose out on some flip-flops. But most of the time you have bigger bit vectors anyway. So while we write the RTL like this, we don't actually get this RTL, and in this case, that's a very good thing. And it does save power. So this is an example where I have the Ethernet. I have Ethernet decoding, then there's an FIR filter, and then there's Ethernet encoding. And there are two FIR filters here. So I'm sort of essentially sending data to one of the FIR filter based on the port. And without this optimization, the FIR filters will not be disabled when their input is invalid. So they will switch all their multipliers, all their registers, and consume power. With the optimization, we only switch the compute logic in the path that is actually being used at each time. And so you can see we get a pretty nice saving in dynamic power. In a more contrived example, sort of a best case scenario, the results look like this. We have without the optimization, if we have the perfect scenario, we can essentially eliminate switching power from being completely unaffected by the validity. So what this circuit is it's 16 multipliers that take a pair of values and then a tree that adds them together. And I should not have a scroll wheel on the thumb of my mouse. The p-valid here is what is the likelihood that each multiplier has valid data. And in this example, in cases where the data is invalid, it's still flipping randomly every clock cycle. And so in this case, we don't make any savings without the optimization. With the optimization, we make a ton of savings by having this by when the sort of chance of data being valid goes down. In a more realistic scenario, perhaps, depends on the application, I would say. If we don't switch the data randomly during invalid clock cycles, we don't lose out, or we still save the switching power without the optimization of the logic, but the switching power of the register still goes down with the optimization on. So you can see the power saving in this other case isn't as good as the previous case, which is like the best case scenario. We're able to eliminate all compute. In this case, we don't eliminate the compute switching power, but we eliminate the register switching power. And so this is something we can do because we have a language that encodes validity of signals in the type system, where the type system, where the compiler and the user are sort of aware of the contract of the types. I don't think this would be possible without this sort of semantic meaning or semantic information. And of course, you could apply this optimization manually, but that requires writing all of your registers like this, which would be super tedious. It also means that if your assumption on your application are wrong, so maybe you thought you were in this case, you thought you were in this scenario, but you're actually in this scenario, then you have to go through and change all the registers. With an optimization, we can enable the design space exploration and sort of change things depending on the application and the input. Any questions on this part?
I have one. This is super interesting. We use options in Chisel, but only for the runtime generation. The hardware itself, the option is, either existing or not existing.
Yeah.
So keeping the option property in hardware is very interesting. Thinking about this, seems like there's some similarities and differences with like a Verilog X don't care. Do you want to comment on that?
Yeah, absolutely. So I think, um,
It's not the same, but there's some overlap, right? So there's some interesting
yeah,
things to think about there.
so there's the way I actually generate this in Spade is um, after this multiplier, there will be a multiplexer that selects between the x and the not x value. And sort of the synthesis is able to do some clock gating. Like you can see the switching power goes down a little bit here. And so you can kind of get some results from clock gating with Verilog, but the results get better when the compiler is more aware and can like generate this hardware explicitly instead of having to have the synthesis tool infer design intent and then do the optimization.
Sure. I guess I was thinking more about the sense for a designer.
Hmm.
There's the recognition of a scenario being a don't care, and then there's the effort a designer puts into actually marking that Verilog as X, right? Where, they
Yeah.
themselves can know this is effectively an X, but not bother marking it X and just turn off or write enable downstream so nothing valuable gets damaged. But the option type, you're, explicitly carrying around this notion this is valid or not valid data, right? It's like it's kind of a interesting feature. Yeah, this is cool.
Yeah, nice. I'm wondering if I think in software there are ways of like optimizing away the option type when it's kind of carried along. I wonder if you could do that in here to like not have to carry the tag along for the ride. But yeah, I think there's lots of fun like stuff to explore with optimizations with higher level HDLs that you can't really do with Verilog.
Definitely. And you can imagine, you mentioned, the synthesis tools, how they process this more efficiently. You can imagine for different targets that might be done differently, right? For example, on FPJ, you may already have an enable on registers anyways, right? And
Yeah.
so,
Yeah, I think that's also an advantage of sort of lifting things from Verilog is that we can kind of there are intricacies in how you should write certain structures. Like Xilinx even have a way of converting clock gating descriptions back into enable signals and stuff like that. And so I think it's kind of nice to lift the abstraction from sort of just infer a register to being explicit about it being a register, because then the compiler can emit register code that is the correct register code for whatever platform you're targeting. And that's something I think Clash does. That they have sort of different codegen for different targets, and I think a few other HDLs do as well.
cool. Very cool. Yeah, this is great. Any other questions in the room? Okay, I think it's okay to continue, please.
All right. Yeah. So my final slide before the conclusion, actually. There's this notion if you talk to hardcore Verilog and VHDL users of if you're using a high-level language, you are sacrificing performance. I think it's kind of not true, but there is kind of a point to it in that we are all compiling down to Verilog. And so if there is a gap, it will be such that Verilog is more optimal than our high-level HDL, right? Because if it wasn't, the user could just write whatever, like exactly the code that we emitted from our compiler, and then they would be identical. So either there is no gap in performance, or there is a gap that makes Verilog or VHDL better. But in a real world, talking about agile hardware design again, if you're writing things at a very low level, you're kind of necessarily putting in a ton of effort to write each design, right? So in Verilog or VHDL, you might only be able to explore a few points on this Pareto frontier of like trading off runtime over area. And if you know ahead of time that this is exactly the runtime you need, then you can, with expertise and time, write exactly this hardware and get like optimal results. But again, agile hardware design, we probably don't know exactly what our runtime requirements are, and we probably don't know exactly how to write these ahead of time. And so it gets expensive to explore a lot of points. In a high-level HDL, where we can do design space exploration and move things around, we can explore a whole lot more points. And if we just look at sort of the points on this curve where the high-level HDL is faster, now we have, or not faster, but better. Now we have several points here where the high-level HDL is in practice better than the low-level perfectly written Verilog, simply because we can explore more points on this sort of design space trade-off frontier. And so I think that's worth keeping in mind, that you don't necessarily sacrifice performance just because you raise the abstraction level a little bit, because you are able to do more design space exploration. So yeah. In conclusion, then, I gave this list of 4 things that I think we need to do with, or that I think we can steal from software in order to build better languages for hardware. Fearless refactoring was the first one, and Spade provides pipelines for sort of trivial retiming. You can refactor your pipelines because you forgot assumptions or because assumptions change. Like I realized a few years ago that a design I built needed way more memory than I thought it would. And then I was like, oh yes, I'm on a Xilinx whatever recent series, so it has ultra RAM, so I'll just use that. And it was super slow. But I realized that ultra RAM can be extremely pipeline. Like you can have 20 pipeline stages and get better results. So because I was able to do this fearless retiming thing, I was able to just add pipeline stages until I hit my Fmax. I didn't have to think, I didn't have to change any code, apart from changing where I put registers. So that was very pleasing. This strong type system is able to encode a whole lot of information. If we realize at some point that our value, which was always going to be valid originally, is now not always valid, we wrap it in an option type. The compiler will tell us all the points in the code where we assumed that this value was sort of always valid. And so we have to deal with them. Otherwise, the compiler won't let us through. So a type system will catch bugs early. And there's like research on this that type systems just catch bugs. So I think that's useful to have in hardware, even if we will, of course, still have bugs at the end of the day. But catching bugs early is so much better than catching them through manual verification, or even worse, sort of after tape out when you have your chip and it doesn't work. I talked about abstractions for hardware. Pipelines is one of them. I haven't talked about this at all, but memories and ports are primitives in Spade. They are not sort of inferred from the code you write. Ports being native to Spade means that you can have a collection of ports going both ways. The ready valid interface that I talked about has the ready signal going backwards and the valid and data going forward, and you can encapsulate those. The compiler will also, through linear types, ensure that you never you set each wire exactly once, so you can't have multiple drivers. And then you can kind of build abstractions in the language. The stream interface stuff that I talked about with Ethernet and CSI and the camera stuff, the compiler doesn't know what Ethernet is. The compiler doesn't know how the camera works. The compiler doesn't even know what the ready valid interface is. It knows about the option type, and it allows you to encapsulate things and add methods. And so you can build abstractions for whatever domain you have, which I think is sort of the thing to aim for in a language, being able to extend the language inside the language itself. I mentioned low performance overhead, right? This is an RTL level description at the end of the day. There's fancy stuff on top, but you can peel off the layers and see the RTL below. And when you need to squeeze out that last bit of performance, you can go back and write manual RTL, even if you don't have to do so all the time. And then finally, tooling. Like I said, tooling is something I'm very passionate about. The compiler, you saw the error messages. I should update those error messages with a new suggestion system. Some other error messages are better than the pipeline error message. And I would say the pipeline error message is still a whole lot better than whatever Vivado spits out. It is a build system, essentially cargo or NPM or pip or SBT, I guess is a Scala build tool. So you can do dependency management. You can you can set up a project with a single command and download all the tools and run it in, well, 3 commands if you don't have REST set up, which is super nice if you're trying to get new people into hardware, because installing the tools for the commercial stuff is annoying. And then, of course, like I said, I built Surfer because I needed it for Spade. When you have complex types, you kind of need to translate those types back into, or those bit vectors back into those types to see them. I needed that, so I built Surfer, and then Surfer ended up being a waveform viewer that a lot of people like. So that's it. That's all I had to say. If you want to learn more, there's spadelang.org. There are other presentations there, and a paper and stuff like that. And if you want to follow me on Mastodon, that's me on Mastodon, or send me an email.
That was great. Thank you so much for this talk. I have some questions, but I want to open up to the floor. Would it be online or in person that people have questions? Yes, in-person question.
Yeah, so you maybe mentioned this already, but is there an escape hatch for IP that is sort of treated as a black box or some existing Verilog or anything like that within Spade? And
Yes, there is. You mark your module with extern, and then you write the sort of Spade wrapper or Spade interface around it. It has a few requirements, like Spade is more linear than Verilog, where Verilog is sort of just a collection of inputs and outputs, right? Spade is more, you take some inputs, you produce some output. And so there are some requirements. Usually what I end up doing is wrapping I have the raw Verilog interface, and I wrap them in a Spade dir interface. But when you do that, it works. Like I've used that quite a bit for projects where, like, for example, I don't want to write a DRAM controller. So I instantiate one that's written in Median, I think. And like primitives for PLLs and stuff is also possible. So yeah, there are escape hatches.
And then one other question I had was, does Spade use an IR? Is it tied into like Circuit or Fertile or these other hardware intermediate representations?
Yeah, good question. At the moment, it's not. The compiler is all internally. I have IRs, of course, because that's how you write the compiler. But I haven't. At the moment, I have my own backend for emitting Verilog. That was very convenient early on, and sort of one reason I haven't gone to Circuit is I don't really want a full C++ dependency, because just being able to install with one command is super nice. But as I'm doing more optimizations and sort of Circuit is growing, I think I will need to join that bandwagon at some point. But up until now, the compiler has been simple enough that I'm just sort of emitting the corresponding Verilog, so it hasn't been priority to switch.
Great. Another question.
So you mentioned that there were some sort of challenges with the type system or with developing with that type system that led you to sort of having to look at the waveforms and build your own waveform viewer specifically for that. I'm wondering if those challenges were, sorry, my brain is slow. What those challenges were and how those compare, or if those appear in other hardware development languages, such as like Verilog or Chisel.
Yeah, so I think I got a question of like what were the challenges in building the sort of integration between the type system in Spade and Surfer, and is there similar integration for other languages? And so once I figured out that I kind of need to build a waveform viewer to do this, like I tried doing it with GTK Wave, and GTK Wave kind of supports translation, but it doesn't support hierarchical translation, which I need when I have structs. So I tried doing a string replacement on VCD first, and tried playing with GTK Wave, and then I was like, okay, I need to write my own waveform viewer to solve this. Luckily, there are people who had done that before, so I could sort of borrow their library. And then essentially, it's not that difficult. Like this Rust having enums makes it quite easy to just, here are all the possible types. I save the type of each variable in the emitted code with a name. Then I just look up that name. What is the type of this? Then I match on that type and sort of do the decoding. It's quite mechanical once the information is there. The downside is I kind of encode the whole compiler state, save it to disk, and then load it up in Surfer, which is kind of cursed, but it's easy. For other languages, I think Verilog doesn't. There are not enough types in Verilog to warrant this. Maybe in System Verilog. Chisel has an out of three surfer thing called tie waves, which I can show here. So this is essentially Chisel integration with Surfer. If you haven't seen that, that might be worth looking at. That translates the Chisel types with Surfer. And Surfer is built like I did not want to write a waveform viewer, so I built Surfer to be extensible so people can do this. And right now it requires a fork, which is annoying. We will have better, sort of easier integration with Surfer at some point, but it is possible. I hope that answers the question.
Yeah, and actually Tieways is new to me, so thank you for sharing this. I'll definitely look into that in a second. Cool. Other questions? So I had a couple questions. So with regard to the notions of having, explicit pipeline latencies, that's very helpful for correctness, right? You can imagine, you drop something in there as you showed, you get things misaligned. What happens if the pipeline latencies are, a range or arbitrary, right? If it has some sort of function, finite state machine or something else.
Yeah. The sort of the pipelining system is flawed in many ways. It works well for straight pipelines, but you do have that sort of problem popping up. There are other languages that have come along, which SUS is one of them, and Filament is one of them that sort of do more with Filament. For example, allows you to have not only reasonable latency but also initiation interval. But I think neither of or all three of us are not dealing with the dynamic latency. Which at that point you kind of need ready valid stuff. I do have I have a broken thing in Spade pipelines now where you can put a register, a condition on a register for that to accept new values, and that will kind of propagate up. The problem is I realized too late that if you do that and you have a sub pipeline, that sub pipeline also needs to know that the main pipeline is stalled. And I couldn't communicate that, so before I do that, I need to add clock domains to the language, which is kind of the next thing I will be working on. And then you will be able to have a pipeline that has a ready, valid, or that you can stall, right? You can have dynamic stalling of pipelines, and that should solve the problem with state machines, maybe. It will become more powerful at least.
Very cool. And then you mentioned this in the talk, I guess, where you're doing retiming, moving registers around very easily because of the way you express them in your language. Do you have any comments on, I guess, how to use that process in a more automated fashion? Let's say, for example, you are using a high quality ASIC tool. You just need to give it the registers. They can do some amount of automated retiming. So I guess that's compatible with Spade. Was any kind of integration there or anything? Or
There's no integration. The RAM example I was talking about, there I just added 20 registers at the end and let Vivado propagate them in. So you could do that. You could turn on retiming, put all your registers at the end, run the tool, see what the results are, change the registers. There's another HDL called Pipeline C, built by a friend of mine, that does iterative retiming, so you're not explicit about the location of the registers. It just essentially, while compiling, it runs the synthesis tool, checks the critical path, inserts registers on the critical path until you meet timing. So Pipeline C does it automatically. In Spade, it's more like you can more easily put more or less registers in there. If you have retiming on, you can put those at the end. If you don't have retiming on, you have to put them where you want them.
sure, this is still a huge improvement. And I guess as you're looking at those tool outputs, try and figure out where you need to add registers. This is a challenge for many languages, I guess. And I don't know, everyone has kind of their own solutions or workarounds. So, post synthesis, the variable names can often be quite confusing. to map that back to the host language? Have you had that challenge in Spade, or how do you deal with that in Spade?
Yeah, I have that challenge. With I mostly work with the open source tools. I'm lucky enough to not have to deal too much with Vivado or the proprietary synthesis tools. And there you can add a source attribute to signals, and half of the time maybe that's propagated. And so if you have a long critical path, you might have like a space source line, Yossi's internal stuff, Spade source line, Yossi's internal stuff, and kind of be able to infer roughly where in your code base the problem lies. That kind of works. I have had examples where it doesn't work very well. It becomes more annoying with like when I started doing recursive methods for iteration, then you get really, really long variable names because it has the whole hierarchy in them, and then I need to figure out something better. I think there's also another tool by another HDL designer. He does very, I can't remember his name now, but that sort of takes a log output, looks for variable name that compiler emitted, source locations that compiler emitted, and translates them back into the actual source line. So if you have like Vivado where you don't have a source attribute, or maybe it does, I'm not sure. But if you get a log file, you can just run that command on that log file and translate things, all the Verilog lines that it spit out back into the things you actually care about in the high-level HTL.
Great. Yeah, no, this is like a common challenge. Everyone's kind of their own solution. It sounds like
Yeah.
you definitely develop and have a good system going.
Yeah.
Another question, which, just to be explicit, I guess, so Spade seems to use the Rust infrastructure. Is it embedded? Is it a standalone language, or?
It's a standalone language. I take the same approach as XLS here of if I don't have a good reason to change the syntax of Rust, I just use whatever Rust does. Because when I tried changing the syntax for stupid reasons, I end up realizing that was a stupid reason in the end. So I think I like Rust, so I'm borrowing the syntax, but it's a standalone compiler, and the compiler is written in Rust because obviously I like Rust.
Great. Yeah, no, we're all excited to go try it out. Any last questions online or in person? All right, let's thank our speaker one more time.
Thanks for having me. This has been great.
Thank you.